Okay, so as we have been discussing this introduction to VLM, we have talked about in lecture 4 CLIP. As I said, CLIP is the fundamental model where the whole revolution started, the visual language model, contrasted learning between images and text pair. Then we talk about COCE and PALI in lecture 4. Then we have lecture 5 in which we cover Flamingo, LLaVA, Painter, and Blip2. So today we are going to talk about ImageBind, LanguageBind, and LLaVA. Okay. Then on Wednesday we'll talk about the Video ChatGPT, Video LLaVA, and PG Video LLaVA. So that's the plan. So let's. Is there a question? Okay. So let's start the ImageBind. Okay. So ImageBind. If you remember, then CLIP, we had this image and the text. So they were put in a same semantic space. So we are binding image and text, right? So here we have representation of image, HI, and representation of text, HT. And we learned this representation so that the correct pair, this image of dog and text responding to the dog, or dog lying in grass, should be similar, it should be closer. And then if I have the negative pair, which is different text, then that should be minimized. This should be maximized and this minimized between these two representations should be closer. In other negative case, it should be far away. So that's kind of idea of the image. So we are binding image and text. So only one pair. So now ImageBind does it the 6 different modalities. Okay, image, text, audio, depth, thermal, and IMU. So these are the 6 different modalities. You are familiar with image. You are familiar with the text. Audio, is another dimension when you speak, and depth is the image where you look at the distance, depth camera, 3D. And thermal is an image where you have each pixel, it gives you a temperature, how hot it is, okay? And IMU is inertial measurement unit, which will give you the accelerometer and the gyro and so on. Like in your iPhone has the IMU kind thing, and all those the watch has, and those kind of things, which will look at different rotation, translations, and so on. So now, what the main point of this paper is that we can bind all these modalities to image and come up with a joint representation. So these are the notations used. So this will be an image, this will be video, different frames, text, audio, depth, thermal, IMU. Now the way we are going to do it is this. So in here we have an image. We are going to bind all those with image. And so text and image will bind. Then we have a 3D. The depth may will bind to the image. And then we have the thermal, also the image, and video to the image. So these will be direct binding because we have the joint pair data set for those, okay? But then we have a video. Now video, as you know, has the audio. So we can go through video, audio, then since video is bind with the image, so that way we will also be able to put this also in the same joint space. Similarly, when you wear the Google glasses or those kind of Apple Pro Vision and so on, that has all those IMUs and so on, other modalities, other sensors, which are also available. The Eco 4D is a data set, which is from Meta, which has the video and audio, images, and also IMU and so on. So that is the binding. Now, as you see, naturally aligned, which means the thick bar is they are aligned because we have these pairs. But now, since we are going to put them in the same space, then it will be emergent alignment, because if the text is aligned to to the image, and if the if the video is aligned to the image, then we have the video aligned to the audio. Then due to that, actually the audio will align to text. Similarly, since image is aligned to this one, which is the thermal, then thermal will be aligned to IMU. So these are the emergent alignment, and these are the natural alignment, which is for which we have a pairs. So that's interesting, right? So it's indirect alignment which we will capture, and that's a main interesting idea in this paper. Okay, so this is like we will have an image, and we will have sheep basking in the sun, and so this is one pair, text and image. This is another pair. We have a depth sensor and image. Okay, so we have like kinetic and these other like LiDAR and so on, which will give you 3D data directly. So they are aligned. And then we have video is aligned with the audio, and we have thermal data aligned with the image, and egocentric video, as I've mentioned, the Ego 4D is aligned with IMU and audio and so on. So, so video audio pairs from the audio data set, image data pairs from the sun RGB D data set, which is available, and then image thermal pairs from the LLVIP data set. This is the person recognition data set from the IR thermal data set, and the video IMU pairs from Ego 4D. So now what we are going to do is take the open clip model, which you will keep hearing that everybody is going to use open clip model, which is trained on these billions of data set image text pairs. And in that VITH, 630 million parameters image encoder, and 302 million parameter for text encoder. And so now once it's trained, and again, it's training exactly same as we did for audio, image and text and clip. So here we'll have more pairs. We'll have the image and the IMU, image and thermal, and all those things, the image and video. So we'll have these which are naturally aligned for those, and then other will be emergent aligned. So now once it's trained, then we can actually do zero shot as we are doing clip. Okay, we don't have to, we can apply to these data set where the network has not seen these data set. That's called zero shot. There's no training basically, zero examples. Okay, so these are the different details about these the classification data set. So you want to take audio and classify what class it is, and these are different classes and different number of samples for the test and so on. So similarly, once it's trained, then we can actually do apply the zero shot on the depth, sun depth, NYU depth, and so on. And this is also for the IR data set. So, and this is for the Ego 4D data set. So these are all testing data set for the zero shot, which have not been used when we train the network. So these are the results, and they show pretty good results. So one is, the first row is the, like, if we don't do anything. So suppose, we have, some number of, say, if you have 100 classes, so if you pick the randomly any class, that will be, 1% of the accuracy. So now if you use the ImageBind, then these are the results. And if you use the text paired, these are the results. So now here is the most important thing, because this is a zero shot. They have not been used. So we can see that we can do pretty well for the NYU depth, 54%, compared to where we use a text pair, like clip kind of thing. Okay? So here also, another data set, we can do 35 compared to 25. Okay? So, and some of these, when they compare the clip text pair, there are no data, results available, so that's why they are blank. Now, of course, this is the SOTA, which means they are actually supervisory trained on those data set and tested. So those have to be high. So it's, I think, pretty interesting that you can take this idea of the clip, because we have only text and image pair, you can extend this to the other modalities, and you can do the interesting thing. So here are the examples. Suppose you can have audio of the crackle of fire, then you can retrieve images and videos which will have some fire. Okay? So here, baby cooing, also you can get the images like that. So from audio, retrieve these images and video. And here you retrieve for depth. Then audio, you can also retrieve your text. Okay? So this, whatever this is, then belongs to here. I say fire crackle while a pan of food is frying on the fire is cracking, and so on. So it's very nice that all these modalities you can do from there. So same way now, if it's in the semantic space, because these are just a vector, right? Each of the image or audio or depth image represented a vector. So you can actually add the vectors. So suppose you take the image here, it's vector representation, and the audio representation of wave audios. Then you can retrieve images where there's a bird and there's waves of water. It's very nice. And same way here, here that you can take the sound of the dog and convert into the text and give that text to the diffusion model, which will generate an image. And so from here, from the sound of a dog, we can generate an image of a dog, which is very nice. Okay? So, and some more examples here. You can take the chirping birds and this image, and you can get these images. And similarly, clapping, and with this image, you can get these, they're having wedding and so on. And church bells and thunderstorm, this one, and the audio of thunderstorm, you can retrieve these. Okay? So also, here is the data set about the IMU, where you have these 6 different parameters with respect to time. And using those, you can also retrieve particular images from here. So as we said, the depth map, the video and images and IR, these are all images. But audio is one-dimensional signal. But you can take the one-dimensional signal and generate an image, which is called a spectrogram, and you can just treat that, all of these images. And same way, IMU is a sequence of these 6 numbers with respect to time. You can capture that, and you can generate an image and give it to these encoders. So it's all in the same framework. Okay, so this was a ImageBind, and now there's another paper called LanguageBind. So if you compare these two, so the ImageBind was the blue one. So we have image to language, we have a depth, we have infrared, audio, and so on. Now here we are going to bind everything to language. Okay, so language here, depth, infrared, audio, and so on. So in particular, they also look at a big data set called VIDL, 10 million data set, with which they use in their LanguageBind paper. And this is actually pretty useful. A lot of other papers are using this VIDL 10 million data set. So as you know, the image data sets is easy because there's one image, not much data. But when you look at the video is a lot of frames. So in 1 second there are 30 frames. So that's why video is hard to store. It requires a lot of storage and a lot of computation and so on. So these are historically data set they are comparing. Like HMD51 has only 7,000 videos, and UCF101 is 13,000, and there are these ActivityNet and so on. But now they had this first data set, VIDL 10 million, which is 10 million data set videos in that. Okay, and in that they have a visual, they have a infrared, they have a depth and audio and language and so on. So which is good. So so in this 10 million, they have 3 million pairs of video and language data, 3 million pairs of infrared and language data, and then 3 million pairs of depth and language data. Okay, so that makes it 10 million. So, and also the last one, 1 million pairs of audio and language data. So everything aligned to the language. Okay, so they went through this whole process of collecting these videos, and this guy Jay is not here. Is he here? Okay, so this should be useful for you. So what they did first is that they came up with some terms to search these videos on internet, right? So they came up with terms from Coco dataset, ImageNet, and so on, and then put those search the text and get those videos corresponding to that. Then they went through, they got this collection. Now they also collected from the sound, the audio, and these are YouTube. These are the two, sources, websites, apps, they collected the audio and the videos, and then they filter them out. And now for the depth and infrared, they actually synthesize these. They generate a synthetic, not the real data set. Okay, so as you saw in the earlier one, in the ImageBind, they were using the real data set. So so these are the kind of searched terms they use. Suppose how to make a delicious chocolate cake, they will type it and get the videos corresponding to that, or the audio corresponding to that, and learn to dance salsa on 10 easy steps, and they got these text labels from ImageNet and Coco and so on. That's the way they did it. So now what they wanted to do, because each of the video, they want to generate these caption, the text, where not all of these have these caption, like these clip data set, which was used image and a text. So they went through these different processes where they put a prompt, they use it, because each of the videos has some hashtag, they will use that, and then they will get some captions, and then there's they improved more captions from here. This is MPlug Owl, is a good model, and getting all these things, then they went to ChatGPT to summarize, to kind of simplify these captions. So this is the kind of caption they will come up with, which will be relevant to this kind of video. So then, as I said, infrared and depth modality generation, they use they actually, I think that they use the gain, because based on some earlier work, the diffusion model came after that. But gain also can be used to generate these images, infrared, and so on, and also the depth images. So then they came up with this kind of data set where they have these pets and animals, sports, news and politics and education, and in all of these they have the hashtag, they have the title, they have the keyframe caption, they have a video caption. So it's a lot of effort to be able to collect in order to train this language model so that you can do these multimodal retrieval and so on. So the method itself is kind of similar to original clip thing. So we have a language encoder, and then we have the video, infrared, depth, audio, and you can put all these modalities if you want. You can keep adding that. And it uses this kind of patch embedding. The tokens are patches, and the way they use this masking also. Some of the mask, they will do a masking of these tokens as we did the MAE, mask autoencoder. And then they have these different, each of these have different encoders, right? There's a video encoder, there's of course a text encoder, infrared encoder, and so on. Now in these ones, they got these initial encoder, but then they fine tune using the LoRA, which is a low rank adaptation of these transformers. So then, given the language, then you can do contrasted learning with video. Given the language, you can do infrared encoder and so on. As we have been talking about that. So let me. So these are their encoders. So again, everywhere you will see the the VIT kind of model transformer used. Depending on how many layers you want to use, what the patch size, and so on. And then, as you see, again the open clip encoder. And so low rank, let's talk about a little bit about that. And low rank is, again, is very common now. So the basic idea is that in these transformers and these neural networks, as we talk about, what you learn are the parameters of the network. Okay? And these parameters basically is the matrix of numbers, like matrix shown here. So these are parameters you learn, you update, you initialize randomly, you update. And so now most of the time they are large numbers. That's why you hear 7 billion, 70 billion, and so on, lots of parameters. So when you want to take the pre-trained model and fine-tune, it's a lot of computation. So the LoRA essentially is saying that how can you make that faster, that you don't have to update all the parameters. Because in these parameters, actually, at the end, there are fewer parameters, not all those billions. So, and since these parameters basically can be treated as a matrix, so now how do we come up with a simplification of matrix so it has fewer number of parameters so that we update fewer number of parameters? So that's the basic idea. So as you have learned before, that this is a matrix, a 3x3 matrix. It has 9 parameters, 9 unknowns, right? Now we can decompose this matrix in 2 matrices. The one is 1, 2, 3. It's a 3x1 matrix, 3 rows, 1 column. And another matrix is 1x3, 2, 20, 30. So this is the factorization of one matrix. Now if you multiply these 2 matrices, then you'll get matrix back. Now in this one, the first 3x3 matrix, we have 9 parameters. But in here, we have 6 parameters. So which means a reduction that we can actually update 6 instead of 9, and that's the whole idea of the LoRA, okay? So what we do, that we have an initial model with W0 parameters, and when we fine tune, we update the parameters, which is with delta W. Now delta W size is same as W because we are adding these element by element. So how can we reduce the parameters in delta W? We don't want to touch the original one that's already there, so we don't have to do anything. But we want to decompose this one. So, so what we are going to do is delta W will break in 2 matrices, B and A, okay? And as we did earlier, so that we can reduce the number of parameters. So here's more examples. So we have input X. So this is the pre-trained weights, W, and this is a delta W. And traditionally, we'll take this X, multiply with W, put WX, multiply with delta W, delta WX, and we add up and that's the updating or fine-tuning of the model. Okay, so now if you look at this is D by D matrix. This is also D by D matrix, which means you have D square parameters. Okay, so which is lot. But if you break it up in these two matrices, A and B, so this is D by R and this is R by D. Now this has dr parameters here, dr parameters here, so total is 2dr as compared to d square. And if R is small, then this will be better. So that's the idea. Okay, so using all that, so they are able to show that this very general model of the LanguageBind can do lots of interesting things. You can do video, you can do audio, you can do depth, and you can do infrared. Okay, so in each of these they have a different data set they try, and then they compare with the clip. Clip was the original model, ImageBind we just discussed, and then other intern video model. So LanguageBind is the blue one. So as you see in all these matrix data set, data problem, they are doing better than all those things. And this is becoming very important whenever you write papers, you have to show something like this. So one is this is a very easy visualization because there are so many things happening. And other is that there's many data set, many methods. So you can put in a table, but this is a very nice visualization. You can qualitatively look at that. Okay. So now we are going to talk about the last piece here, which is LLaVA paper. It was Visual Instruction Tuning title, and this is very fundamental paper. This had a big impact. So last year when I covered this, at that time it has 660 citation. In 1 year, now it has 4,749 citation. You can see how it has gone up. So LLaVA stands for Large Language and Vision Assistant, and is a first successful image text conversation model, and it does instruction tuning. So far we haven't talked about instruction tuning, and we are going to discuss that. Very important idea. And so what that means, that these models we have discussed, say large language model, it will basically predict the next word, right? And for the clip and so on, it will just give you representation, then you can solve the problems like classification, question answering, and so on. But when you want to build the chatbot, like ChatGPT, so ChatGPT is built on top of the large language model. So it's not only large language model, but it is large language model which is instruction fine-tune, so that it can, instruction fine-tune means that there's instruction to the large language model, there's a question, there's an answer. So you give instruction, question, and answer. So you give instruction, question, and ask large language model to predict the answer. And you have a ground truth answer, and you want to compare. So you make it that once it's trained, the next time you ask question, it will answer using the whatever it had learned from the language. So this is you're making from large language model to chatbot, from GPT to ChatGPT. So that's the main idea of instruction fine-tuning. Okay, so so now in order to do that, all these things you will hear, you need a data set for everything, right? So you need to have instruction following data. And so now this is a visual language model. So we want to, we have an image data set and all this thing, but we want to take the image, text, and we want to convert in the instruction tune data set, which means we want to come out with question answer. Okay, so given an image, you want to come up with what question you can generate from that image, and what should be the answer we train like that. Then the VLM will learn, and the next time you can ask any question, will answer that. So this achieve at that time pretty good accuracy on the science question answer. So another benchmark, which is about 20,000 multimodal multiple choice question. It will be image multiple choice question. You select which one is correct. Okay, so there are two kinds of multiple choice question. Other is general question, open-ended question. You can ask an open-ended question, answer. So multiple choice question is easier, and it's easier to evaluate, but it's limited because you will give answers. Like you take the test, multiple choice. Test is very easy, right? But and you cannot do much. But the real exam is you are given a question, you answered, you write, figure it out. So the same thing. So open-ended question answer is harder, but then evaluate. How do you evaluate? You have to ask humans to evaluate ChatGPT and so on. So they had this 21,000 questions and 3 subjects, 26 topics, and 127 categories, and 379 skills. Okay? So, and LLaVA architecture is very simple. So you have an image, and it goes to the image vision encoder, and you get the embedding ZV. So this is image. Go to the image encoder, get a representation of that, and the image encoder can be clip encoder. And then you have projection layer, W. So then you take the ZV, apply this projection layer, and become HV, which then goes to the large language model. So again, similarly, we have a language instruction, XQ. You go to encode it HQ, and so these are tokens from image, these are tokens from text, and then goes to language model, and you get a response, which is answer, XA. So XQ is the question, XA is the answer, HV is the image. Okay, so it's a visual language model, LLaVA architecture, very simple. So, so in this one, first step is that we want to pre-train for the alignment of features. So you want to align these image features with the language features. So essentially, you want to train this projection layer. Okay, so for that they use these dataset CCM3 with the filter to these numbers, image text pairs, because CC3M is a very large data set. And so they kept the visual encoder and the LLM weights frozen, and then trained for the projection layer. Only this one, it's a linear layer. Okay, so theta is the parameters of the projection layer. So then you want to fine tune end to end. So now you want to basically train the update, the 5, and also W. So 5 are the parameters of the language model. Okay, so so this will be the format of that. So you have the human will say instruction 1, and then assistant, your chatbot will give you the answer. Then will be a series of those instruction, assistant, and all this thing. So the system message is, you will give the instruction to the chatbot, a chat between a curious human and artificial intelligence assistant. Assistant gives helpful, detailed, and polite answer to the human's question. So for each image X, so we will have these question for image 1, answer for image 1 and 2, and so on, all these total T images. So it will pick randomly first time. These are different turns, So first time it will turn randomly whether you can pick the question first and the image, or image and the question, but next thing you will pick the the question, and you keep doing this because you are asking the same questions about the same image, many different questions about the same image. So these are different turns. So now the way you train is again pretty simple. That you want to, given the so this language model will predict the answer, right? XA. So suppose you have already got answer up to I minus 1, XA less than I, okay? And you have done this instruction up to I minus 1. Now you want to do this instruction and this image, you want to predict what should be the next token, and that is the way that's the way you actually take this loss function for all these 1 goes to L, and you keep minimizing this loss function, and that's the way you do instruction tuning. So again, this is the answer, this is the image, and this is instruction, and you want to predict the next answer. You already have answer up to I minus 1, and you have instruction up to I minus 1. Then you have the image and instruction. You want to predict the next answer. So that's the way you do the instruction fine tuning. Okay. So let me move this up here. So so they use a COCO image to generate 3 types of instruction following data. So suppose you want to do conversation, just ask question, give you something. Other is detailed description. Other is complex reasoning. And then since it's the image, so you can get the captions, but in addition to that, you can detect objects in the image and generate question answer pair from there. So that they are also doing that. So we have 150,000 unique language image instruction following samples, and 58,000 conversation, 23,000 detailed description, and 77,000 in complex reasoning. So suppose here's the example. So there's an image here, and captions of this image are shown here. A group of people standing outside of a black vehicle with various language and language surrounds a vehicle and all those things. People fill their luggage in SUV and so on. So you will take this image from the COCO and generate the captions for that. There's a separate, method will generate caption. Or you can ask people, humans, write a caption, right? So that is the caption. And then in addition to that, you can take an image, give it to YOLO or the FOSSA scene and so on. It will detect objects, give you bounding boxes. So it will also recognize, say, well, there's a person at this bounding box, another person this bounding box, and so on. There's a suitcase, there's another suitcase and car. So this also you give it to this VLM, okay? So caption boxes are used to promote. Now you give caption and the boxes GPT to ask it to generate question answer pairs, okay? So the interesting thing is that, before GPT, we were not able to do those. So once GPT showed ChatGPT that you can do a lot of things, now we are building the next generation of the chatbots heavily relying on GPT, that it can give us this data to train a new VLM, new chatbot, and so on. So which is very nice. So now, in order to generate discussion answer pair for this LLaVA, you actually are not using the image. You take an image, you get the captions, and you take an image, you get these bounding boxes. You give those bounding boxes information and the caption to the GPT, it generates question answer pair. Okay, so that's I think the difference here. So now conversation can be like this. What type of vehicle is featured in the image? The answer will be the image featured a black sport utility vehicle SUV. Next question will be it's a turn, different turns of this question. Where is the vehicle parked? The vehicle is parked in an underground parking area. What are the people in the image doing? The people are trying to fit all of their luggage and so on. So then another type of thing they are looking for is detailed description. It will describe, the image is underground parking area with black sport vehicle and all this thing. So these are kind of conversation you can do with the chatbot. You want to, this is the data they are generating. You'll train the LLaVA using instruction following data. Then next time you can ask similar questions. Okay, so this is another complex reasoning. So reasoning means that it can come up with the answer, but you want to ask some deeper question. So why is it happening? So suppose you're saying, what challenges do these people face? So so it's going through talking about multiple suitcases, backpacks and so on, which suggests that group has a significant amount of belonging to accommodate. They might have strategies and arrange luggage. So this is, is talking about more detailed, complex reasoning, what you see in the image, which is very interesting. The machine is doing that, right? So, so here are the different prompt, different instruction they use. For image description, you can say describe an image. You can say provide a brief description of the given image, offer succinct explanation of picture presented, summarize the visual content, and so on. So because see the people, you want to make this thing that you can type anything, right? So these are kind of covered what person, any person will ask potentially this question about an image, render a clear, concise summary. So that's an interesting thing. Otherwise, it's not limited. If you just train only for the image concisely, then it will be very limited. But they are using all those things. And all these things you can ask GPT to generate for you. Okay, so similarly, they have these kind of things for detailed description. So describe following them in detail, provide given image, give an elaborate explanation, all kinds of walk through the important details of image, portray an image with a rich descriptive narrative. You can keep on and on. So here's an example from LLaVA. So this is an image given, and then it's asking what is unusual about this image. So it will go through, describe that. Okay, so it's that during testing, they've already done the instruction fine tuning. So, so which is pretty impressive that the computer can do that for you. So all that is power of the large language model, because large language model is so much information. Then VLM, what you're doing, take an image, encoding it, converting tokens, and then putting in large language model, and you are then instruction fine-tuning, that if this is a question, answer should be this. If this is a question, answer should be this. It learns, and then you can test it. Okay? So, so this is another example here, that you give an image and then with the text, so this both goes to the LLaVA, and then you ask this question, can you explain this meme in detail? So talking about these chocolate chip cookies and map and earth and so on, so you can do that. Okay, so now LLaVA, as I said, it was the first VLM, which shows that you can go from one of the first one to go from the ChatGPT, which is purely language, to this image input, and there's a lot of follow-up work on that. So after LLaVA, there's a paper called LLaVA 1.5. Then there's a LLaVA Next, and there's a LLaVA 01, and there's a video LLaVA, which we'll talk about on Wednesday also. So let's quickly go through LLaVA 1.5. So they made small changes, but it made a big difference. So instead of the linear layer, the projection layer, they introduced the MLP, the multi-level perceptron, which has multiple layers, and the the nonlinear ReLU and so on. So then they also use the more data sets compared to what they were using before in LLaVA. And also they were able to include the high resolution images. And then they made some changes in formatting when they were prompting the LLaVA, and that made a difference. So as you see again, it's the structure is same. You have the video encoder, and then here you have MLP, multi-level perceptron, and the language model is same, and then you have text tokenizer embedding. Okay, so for including the higher resolution images, what they did, take an image split in 4, then separately encode each pieces, and then also take the image, reduce the resolution, encode that, and take all those, put those tokens, as compared to what we are doing. We were putting just in the LLaVA just one resolution, and this we were not able to incorporate many tokens. Now here, this number of tokens here is same as the number of tokens in the original image in the LLaVA. So we have more tokens and more information. So that's one. And prompt formatting, there was confusion. Suppose if you have given this, so is this unusual? Please explain in detail. So sometime it would say yes, it was not clear. So what? Suppose you can have what is the color of the shirt that man is wearing. So it's put A means answer. Then say man is wearing a yellow shirt. So normal prompt, what is the color of the shirt that the man is wearing? Then we'll answer like that, man is wearing yellow shirt. But they change the formatting. They actually put this thing. What is the color of shirt that the man is wearing? Answer the question using a single word or phrase. So just answer yellow. So otherwise it was confusing. Sometimes it will give this, sometimes it will just say yes, and so on. So that also made a difference. So here are the comparison. So now this is the LLaVA, the original LLaVA, and they show you which LLM, how big the LLM they use. They use 7 billion, and these are the different metrics. And so you can see that when they added this new data set VQA, same size of the image and same LLM, so it made a difference, right? 809 to 1197, 27. Then they changed the prompt formatting, as I explained, so that also made some difference here. And then when they add the MLP, that made a difference. And they get another data set, OCR, made a difference. So they did some more things, scale up resolution, talk about, and increase the image size from 224 to 336. Then they added this GQA, another data set, and ShareGPT, and increased the LLM from 7 billion now 13 billion. So that made a difference. So that's improved version of the LLaVA, which is LLaVA 1.5. So now that is able to do something like this, that you give the license person, and these are the instruction that then you want to get output, okay, in JSON format. So they're comparing with LLaVA and LLaVA 1.5. So most of the time it's able to get correctly compared to LLaVA was missing. It was putting this garbage here and so on. So now, of course, if you keep hearing that this closed source model like GPT-4, we don't know what exactly they are doing. And GPT-4 is always in performing better, except there was a news last few days. There's a DeepSeek model from China. It's kind of beating GPT-4 Google model also, and open source. So that's the big change is happening, and probably due to that, today the U.S. stock market went down. It has a big impact that the open source models are doing so well, and in China, so all these companies, AI companies, U.S., so that is the race in AI happening. And actually there was Anthropic is another company. They're doing very well. So there's a big yearly conference in Switzerland, Davos. So Anthropic CEO said that in 2 years, the AI models will be able to do all the things, or maybe even better, what humans are doing. So this is, big disruption is going to happen. That the things are going so fast that, in one way, it's very exciting that you are learning all those things, in this class. In other is that, what's going to happen. A lot of things are going to change, a lot of jobs are going to change, but more jobs will be created and so on. Okay, so this was LLaVA 1.5. And see, the interesting thing is that you can get all these things and then you could use it. I saw a video last night also. This guy, he got the DeepSeek version 1 or R1 or something. He wrote a very simple instruction. He was able to generate the image of the world for top 10 cities which are popular for tourists, their population, all the details. Just for putting few commands to DeepSeek, and it did it. So it wrote the code itself, right? So that's again, being computer science. So the issue is that whether next 10 years, after 10 years, we'll be teaching coding or not, because if these AI models are doing coding for you and works very well, so it's a huge disruption. Okay, so then there was another method called LLaVA Next. So that has improved reasoning, OCR, and word knowledge. So there they were able to increase the resolution, 4 times as much to this resolution, and they had a better OCR, which means you can read the letters because that's a harder, right, very small, and also better conversation. Okay, so then there's another model called LLaVA 01, which is the reasoning steps. So we'll explain to you how it got that result. So that's called chain of thought, reasoning, and that's also becoming important because if the AI model tells you something, but how do you rely on it, right? If it's an important decision make, but it tells you how it, reached at that point, then it's more, comfortable. People are more comfortable with that. And also, this reasoning can help you to get the correct answer. So that's another big area, and that's what the DeepSeek R1, they use the reinforcement learning to really improve a lot. So here's an example of reasoning. So we have an image, and so question is, subtract all tiny shiny balls, subtract all purple objects, how many objects are left? Okay, so then there are these options. So this is a multiple choice question. 4 and 8, 2, D, A is 4, B is 8, C is 2, and D is 6. So this will be from LLaVA, 3.2, 11 billion. And it has some reasoning, but it came up with a wrong answer. Okay, so which is C, which is 2, but the correct answer is the 8. And here, this LLaVA 01 come up with the correct answer using, first we'll summarize then we'll get a captions, then we are reasoning stage, how to solve the problem step by step. First I will count all the objects in the image. There are 10 objects in total. Next I will identify and subtract the tiny shiny ball. There is one small shining green sphere. Then I will identify and subtract the purple objects. There's one purple cylinder. By subtracting the 2 objects, shiny ball and the purple cylinder, the total I find 8 remains. So pretty interesting. That's the way you do it, right, humans? So this is what the language model is doing. Okay, so I think that's what